Okay, here we go. So I'm going to talk to you over the next 15 minutes about how we can use aerial photography or photogrammetry to ask questions about the health and condition of large cetaceans. And I'm going to give examples on blue whales and gray whales and also on right whales. Eeks. Okay, so what I want to talk about today, I'll briefly talk about the technologies we use for aerial photography, and then I'll get into 3 case studies. I want to talk about gray whales, right whales, and blue whales, and finally I want to talk just very briefly about options we have for platforms we can use to collect aerial images. Photogrammetry has a very long definition. It's really about everything associated with collecting aerial images and how you interpret information from the objects that you photograph, their size and their shape. Today, again, I'll talk briefly about the technology of photography and then focus on data we've taken from aerial photographs of large cetaceans. This is probably the only military slide you'll see today at the symposium. These are wonderful old cameras that we got from the U.S. military. We've used them for a couple of decades. They were really the best thing going for low altitude, high speed reconnaissance. But frankly, the days of film imaging are over. None of us can afford film. None of us can get it processed anywhere. So the digital era is upon us. And also these cameras were almost as old as I am. They require radar altimeters for scale, separate DAS systems, so you're running computers in parallel with these things, fancy power systems to make them go. So it was really time to move on, and actually moving on has been a very positive step. The new digital systems produce images of higher quality. In addition, they're much, much simpler. This is a system based on a Nikon D700. You can hook a sophisticated GPS unit directly to this camera. It'll record position and altitude as part of the metadata for each frame. So now it's much, much easier to go in the field and collect data. I didn't want you to have the only shot of a reproductive female in the whole presentation. Oh, am I wandering away from the microphone here? Sorry. What you see here are 2 examples of how reproduction affects shape in female mammals. Claire on the right just had her baby 5 days prior to this, and Gabriella's about 5 days from having her baby, and you can see their reproductive situation affects their shape. Well, female humans feed during all of reproduction. They feed through lactation, and so really the changes in shape associated with reproduction in humans are not nearly as dramatic as the changes in shape associated with reproduction in large cetaceans. And that's because most cetaceans are what we call capital breeders. So these are animals that will go to the feeding grounds and invest in capital in the form of fat, and then during lactation they'll draw on that capital, and that causes them to become thinner or change in shape. And the first step in most photogrammetric studies or photographic studies where you try to see how animals change shape as they lose weight are based on looking at these predictable changes in shape that happen to reproductive females. So the first case study I want to talk about is on gray whales, and I'm going across the equator here. We're going to talk about the northeastern population of gray whales. These are animals that feed in the Arctic and then migrate all along the coast of North America down to the lagoons off Baja, and then turn around and return back to the Arctic. And the data that we collected and the data I'm going to talk to you about today were collected here in Southern California. This is right at the end of the southbound migration, and then we catch the animals again as they turn around and start to migrate northwards towards the Arctic. The changes in shape in gray whales from being pregnant and giving birth are really obvious. The panel on the right, whoopsie, this animal over here is a near-term, hold it, I almost got it. This is a near-term pregnant female, and she's clearly shaped differently than this other southbound gray whales. And what we've done is develop a condition index based on the relationship between the maximum width of the animal and the animal's total length. And the data I'm going to present to you in this next slide are taken from photographs we collected in 1996 through 1998. Okay, these are length and width data from gray whales On the y-axis, whoopsie, on the y-axis over here is the relationship between width and length. So animals that appear up high here are very wide relative to their length. This line in the middle of the slide separates data collected from animals migrating south from animals migrating north. And as you can see, pregnant females are very, very wide relative to their length. Postpartum females are also wider than the average animal relative to their length. And down here is the rest of the crowd, the adults and juveniles, which are more narrow. What's interesting here is these two sets of data are collected about 45 days apart from one another. This is a 45-day period in which animals are fasting, and we can detect a significant difference in thinness of whales just based on about 45 days of fasting. And the skinniest animals at all are the northbound females. These are females who've been lactating for about 3 months, and so they're by far the thinnest of all the animals. So from phase 1, we found that we could clearly detect changes in reproductive condition in gray whales from measurements and aerial photographs. That's kind of low-hanging fruit. We also found evidence of the same pattern of segregation by age and reproductive condition in migrating gray whales as Rice and Woolman found from whaling data. One of the advantages of doing this kind of work is all the history data kind of free add-on to the condition information you're collecting. We also found that we could tell the difference between southbound and northbound adults and juveniles, the north ones being thinner just based on about 45 days of fasting. But the real question is, can you use measurements from aerial photograph as a primary data source for tracking population level changes in condition in gray whales? Now, we were fortunate, thanks to a lot of support from Bob Brownell, we were able to continue sampling southbound gray whales from 1997 through 2003. In 1999 and 2000, strandings of gray whales increased from an average of about 25 to over 300 animals per year for these 2 years. So what we wanted to know was, can we use aerial photographic sampling to inform us on the underlying cause of this mass stranding event? These are data of widths and lengths for gray whales that we can from 1997 through 2003. On the y-axis, again, means of the relationship between widths and lengths. And what you can see is that in 1999 and 2000, the years that we had very high stranding rates, gray whales were significantly thinner than they were in other years. So part of the underlying cause of this mass mortality event we had in gray whales was probably related to a significant drop in overall population condition. Okay, I want to get into the second case study, which is on right whales. This is work that was done by Carolyn Miller as part of this at Woods Hole. She was a little less arbitrary than we were on where she measured the animals. She looked at right whales, and clearly maximum width wasn't going to work for that animal. So she came up with another technique. And she also decided that if you're going to look at how animals draw on curves, you don't want to just sample them on the feeding ground. You want to sample them on the feeding ground and on the calving ground. So she worked both with North Atlantic right whales, and then she also worked with Peter Best on southern right whales. So she came up with a technique for measuring widths of animals. What she did, broke the animal into several sections, each one about 10% of total width apart, and she measured their width at 8 of those sites. And then she compared width and length for a wide section of animals and did a principal components analysis just to see what was the most informative place along the length of the animal. What told you the most about how much weight they were losing. She did something else that I thought was really clever. She also did some work where she looked at animals that she could identify and looked at how they changed in width relative to length. And if you look at the top figure there, this is for a female. This was sampled once about a month after she gave birth and then 3 months after she gave birth. The blue line represents what her shape looked like right after birth, and The red line represents what her shape looked like after about 2 or 3 months of lactation. And as you can see, she got skinnier, which you'd expect, but the change in width was mostly back aft here in the latter part of the animal. So what she found was that looking at data from several sites along the body, the most informative place was about 60% back from the rostrum in total length. That reproductive females thin significantly during lactation, which is what you'd expect. And she also took an individual-based approach to monitoring condition, which I thought was a really interesting step. Okay, the third case study I want to talk to you about is on blue whales. This is an effort that we're doing at the Southwest Fisheries Center, and it's still underway. We first collected aerial photographs to ask questions about size and body proportions of blue whales, because we really didn't know what flavor of blue whales we had off the coast of California, and that's work that Jim Gilpatrick and I published in 2008. Currently, we're looking at both film and digital images of blue whales off the California coast, trying to establish sort of a baseline data set on size and shape for blue whales. These animals are a little more difficult to work with because they feed year-round, so you don't have the dramatic changes, but for a fasting whale like a gray whale. So the first work we did, we looked at how the length of the rostrum and the distance from the dorsal fin to the fluke notch compared relative to total length for these animals and for animals taken in historical fisheries. And this is just a panel from the paper that Jim and I published. And in the top panel you see this is the rostral length data, and these are data for ordinary blue whales from the whaling industry. These are data from pygmy blue whales, and as you can see, our data off California fall right in the middle between the two of them. There's no difference in the front end of the animal. But if you look at the lower panel where we looked at the distance from the dorsal fin to the tail fluke notch, you can see that ordinary blue whales had a much longer tail stalk than the animals we have off California, and that ours are really identical to the blue whale. Okay, now to the condition work that we did. That Carolyn took, where we measured the animals at several spots along the body. And these are data that, again, on this axis, it's your average, it's your width divided by your length. And I have two groups of animals. The little blue triangles are for females with cows, so these are lactating females. And the green squares are for the other adult-sized animals. We took all the small animals out of the sample. And we measured at several spots along the length of the animal, starting about 30% back from the rostrum and going all the way to 70%. What we're looking for is where these two little figures separate from one another, and lo and behold, it's right here at about 60% of body width, just body length, just like Carolyn found with the right whales. So if you want to look at how blue whales change in shape as they lose weight, you want to look quite a ways back on the animal. So what we've learned from all this photographic work is that, you know, if you want to ask questions about how animals change shape as their condition changes, you have to decide what question you're asking. Are you asking, is it a pregnant animal, or are you asking whether it's a skinny adult animal? And in both cases, you probably want to sample at several sections along the animal to be sure you're getting the right spot to answer your question. Questions that you can ask about a population, about its reproductive or nutritive condition, depend on when you're sampling, whether you're sampling during the breeding season or whether you're sampling during the feeding season. And also, clearly shape changes significantly during each of these seasons. So if you want to monitor change in condition across time for an animal, you want to be sure that you sampled it about the same time every year, because otherwise you could mask your signal. Finally, I just wanted to mention that, you know, there's some places where you just can't get manned platforms to do aerial photography. But these modern unmanned platforms now become so reliable and so efficient that we really have other options for collecting data. I'd love to land one of those in the back of one of those sleeping humpback whales. That'd be really cool. Thank you very much.